Right now, somewhere in the world, a missile is being developed that no defense system on Earth can reliably stop. Not because it's invisible, not because it's nuclear, but because it moves at 25 times the speed of sound. That's New York to London in 12 minutes. And here's the thing nobody talks about. It's not just the speed that makes it unstoppable. It's where it flies and how it thinks. Today, we break down exactly how hypersonic missiles work and why they're changing warfare forever. Let's start with what hypersonic actually means. You've heard supersonic. That's anything above the speed of sound. Mach 1, about 1,235 kilometers per hour at sea level. Hypersonic is a completely different category. Mach 5 and above. That's 6,100 kilometers per hour. At that speed, the air in front of the vehicle doesn't have time to move out of the way. It compresses, it heats up, and the vehicle punches through it like a hammer through paper. There are 3 types of hypersonic weapons you need to know. First, ballistic missiles, the old threat. They go up, come down, and follow a predictable arc. Second, hypersonic glide vehicles, or HGVs, launched by a rocket, then released to glide through the upper atmosphere while changing direction. Third, hypersonic cruise missiles, powered all the way, no ballistic arc, just pure sustained speed. The last 2, that's the revolution. Here's where the physics gets extraordinary. To sustain hypersonic speed in the atmosphere, you need an engine that doesn't carry its own oxygen, because at Mach 5, the air rushing in is the oxygen. That engine is called a scramjet, short for supersonic combustion ramjet. In a normal jet engine, air comes in, slows down, mixes with fuel, burns, and blasts out the back. In a scramjet, the air never slows down. Fuel is injected directly into a supersonic airstream. The combustion happens in milliseconds, at speeds faster than a bullet. The result? Sustained thrust with no moving parts, at speeds that would melt conventional metal. But scramjets only work above Mach 4. Below that, they produce no thrust at all. So here's how it works in practice. A rocket booster accelerates the vehicle past Mach 4. Then the scramjet ignites, and the missile continues under its own power, low, fast, and nearly silent on radar. Hypersonic glide vehicles take a different approach. The rocket launches them to the edge of space. Then they re-enter the atmosphere and glide, skimming the upper layers, converting altitude into speed. Here's the problem that nobody solved until recently. At hypersonic speeds, the air around the vehicle doesn't just heat up, it ionizes. It turns into plasma. A sheath of superheated gas glowing at 2,000 degrees Celsius wraps around the entire missile. That plasma blocks radio waves. Your GPS signal, gone. Communication with command, cut off. And that same plasma makes the missile almost invisible to conventional radar. But the real nightmare isn't the speed. It's the combination of speed and maneuverability. Traditional ballistic missiles follow a predictable arc, like a cricket ball. You can calculate exactly where it's going to land the moment it launches. A hypersonic glide vehicle can change direction mid-flight. Interceptors are designed around predicted trajectories, but a vehicle that can bank, dive, and redirect at Mach 10 gives you a firing solution that's obsolete before your interceptor even leaves the ground. The window to intercept? Less than 3 minutes. So what actually holds these things together at 2,000 degrees? The answer is materials science. The leading edges of hypersonic vehicles, the nose cone, the wingtips, the control surfaces, are made from carbon-carbon composites, carbon fibers woven in a carbon matrix. These materials can withstand temperatures above 3,000 degrees Celsius, and they actually get stronger as they heat up. Some vehicles use ablative heat shields, materials that deliberately burn away in a controlled manner. As the outer layers ablate, they carry the heat away from the vehicle, like a self-sacrificing armor. And control at these speeds doesn't come from traditional fins. At Mach 10, control surfaces barely work. Instead, engineers use reaction control systems, tiny thrusters that fire in precise bursts to steer the vehicle. The result? The hottest, fastest, most maneuverable object ever placed in the atmosphere. So how do you stop something like this? The honest answer, right now, nobody reliably can. Traditional missile defense systems like THAAD and Patriot are designed for ballistic trajectories. They're optimized for the predictable arc, not the low-altitude, high-speed maneuvering threat. Space-based sensor networks are now being deployed specifically for hypersonic tracking. Satellites watching the heat signature of a glide vehicle from orbit, covering the entire trajectory. The US is developing the Glide Phase Interceptor, designed to hit hypersonic vehicles during their most vulnerable window. Russia already has the Avangard glide vehicle and the Kinzhal air-launched missile. China has the DF-17, specifically designed to threaten aircraft carrier groups. The race isn't just to build these weapons, it's to understand them well enough to stop them. The scramjet, the glide vehicle, the plasma blackout, the 3-minute window. These aren't science fiction, they are the physics of a new era of warfare, playing out right now. And here's the question that nobody in defense is sleeping easily over. If the offense has moved this far ahead of the defense, what comes next? If you found the physics in this video as mind-bending as I did, wait until we talk about how electronic warfare tries to blind these weapons before they even launch. Subscribe and I'll see you there.